Okay. I know there's a lot of videos and recordings up, but working in a group and all that, I think that's going to give you more, good stuff. You'll learn the stuff better if you do that. So try to make it to class. I'll keep a list of who shows up, and at the end of the quarter, if you're borderline and you've missed half the classes, then I won't be very generous. But if you came to all the classes and you're borderline, I'll move you up. Let's see. And I couldn't tell. Let me ask one more time. Last week, how many of the 348 classes actually had a lab where you did characterization?
I had an actual lab.
An actual lab?
Yeah, I had one too.
Okay. All right, then this week you're probably doing current mirrors, which if I went with our regular pace, we wouldn't get through till Wednesday. So I'm just going to talk about the lab topic first, and then we'll go on and finish up the small signal model. Let's do this. And let's see. Actually, I should remove this. So ignore this for a second. Move this out of the way. Oh, and also my headset was supposed to already be here this morning, but it's not. Somebody's delivering it to the house. So once again, the birds are, I gave them a new toy thinking they would shut up if they had their mouths full, but apparently that's not working. So our goal, the first amplifier we're going to build is this one. And hopefully you recognize it as a common emitter amplifier. And everything I say about the common emitter amplifier is true. Is true for this amplifier. And again, what's that amplifier called? You X out the terminals that have V in or V out on them. Whatever the leftover terminal is, it's a common that thing. So what's this? Common. Is it a common gate?
Common source?
Common source, exactly. And we'll do the math for the MOSFET after the BJT, but it's pretty much exactly the same math, except you use a different current equation. Okay, so our first goal is to build this common emitter amplifier. And if you look at, scroll this over, you look at the VTC, the VTC looks something like this. And if you have V in too low, let's say you have V in equal to 0, how much current's going through your transistor?
None.
None. And if there's no current going through the transistor, how much current's going through the resistor?
None.
None. And so the voltage drop across the resistor is?
0.
0, which means V out equals, somebody just said it?
VD.
Yeah, so you're over here. And that doesn't do you any good. That's not an amplifier. What if I make V in really high, so there's a ton of current going through the transistor? Where are you on this graph?
Like where V out is 0, around 0.
Yeah, you're way over here, and that's a lousy amplifier too. So if you want this to actually act as an amplifier, you want to be in this region right here. So to do that, you want your V out to be sitting somewhere in the middle here. And so what you do is with an amplifier, the first step to building an amplifier is to set a default current through your amplifier. So you set the VBE here, set VBE, set VBE such that let's call this, I'm going to call it VDD over 2, though that's not where you actually want to bias this. This is not where you actually want to set V out, but just for discussion right now, that V out VD over 2, and you know V out, sorry, let me get rid of the nail. And you know that is VDD minus I times your R. So the first job that you usually do with an amplifier is pick a current. So when there's no moving signal, and that's weird because usually V in right here, you've got a signal coming in and it gets amplified. We're gonna assume that we just are trying to find a DC voltage here that sets V out at this VDD over 2. Okay. So up to there, any questions? Oh, okay. So let's see how you set a DC current through your amplifier. And a slight pet peeve of mine is that this circuit, this current mirror circuit, it's introduced as a current source, which it is, but the whole reason why we're introducing it right now is to set the current through your amplifier, so your V out will sit at the point that you want it to sit at. So we're just trying to set a default current through your amplifier. Okay, so let's go on to step 2. So I generally divide up this current mirror into 2 parts. There's 2 parts to a current mirror. This whole thing is and happens here is this part of the circuit, it's a calculator. It calculates VBE for a current. Okay. And the way this works is you force the current that you want I out to be. So we call it I ref on this side, because later on you can make it so the 2 currents aren't quite equal. but um, you force a current through the transistor, and physics happens. And for whatever that current is, this actually moves to the correct VBE for that current. So this happens to all transistors in the active region. If you force a current through the transistor, VBE will magically go to the correct VBE for that current. The question is how to force the current that you're targeting, how to force that current through this transistor. This may seem a little bit hand wavy, but this works. This VBE, for different currents, the VBE is going to be a little bit different. Is it going to be a lot different? What happens to the current if VBE changes a lot?
The current will change exponentially.
Current changes exponentially. So this VBE right here doesn't, it is different than VBE on, but it's not very much different than VBE on. It's pretty close to VBE on. And all quarter, for most calculations, you can just approximate that as VBE on. Okay. So if we're approximating this as VBE on, and you have some target current, how would you find R?
Well, the voltage in the node after the resistor is connected to the base. So whatever your base voltage is, well, VDD minus I reference times R should be equal to the base voltage.
Perfect, yeah. This is important. This is this connection from the base to the collector, which is called a diode connection. And that's a diode connected transistor. That sets the collector to the same voltage as the base. And now you know that the voltage across the resistor is VDD minus VBE on. And if you have a target current, now you have the voltage across the resistor, you have your current, and you can find your resistor. And you say, well, wait a minute, VBE is not going to actually equal VBE on. It's going to equal it's going to be pretty close to it. And this generally gives you pretty close to your target current. Okay. So if you force that current, through your transistor, now your transistor physics happens and a VBE magically goes to the exact VBE that is needed for that current. And now if you use, so now this VBE is now the correct VBE for whatever current you force through here. Now if you use this VBE on another transistor, your I out will equal your I ref. It mirrors the current.
I have a question.
Okay.
So is VBE on the transistor to the left, is that voltage actually VBE needed to get that current, or is the voltage VBE on? Because
It's the,
what was that?
It's the voltage for that current. You can
So
use,
sorry.
I'm having trouble hearing you again. Let me turn you up. Okay, you're on full blast now.
Okay. My question is, you have there that it says VBE on, and my question is, VBE on, that voltage will not produce the desired current all the time, right? So that VBE will change in accordance to what current you want coming out.
Mhm.
So is that voltage actually VBE, or is it VBE on?
It's actually the VBE for the current. And the reason why you can do this and why this is pretty close is this node right here will change some with the change in the current. Your VBE will change a little bit. I agree with that. So it's not going to be exactly VBE on, but it turns out resistors react much less when you change the voltage across them. What I should say, there's not all that much of a voltage change across it. So the current through the resistor is going to be pretty close to the current you're targeting if you use VBE on here. Let me try to say that better. Anybody say it better? Let's say VBE on is 0.7. And you approximate that as 0.7. Okay. Now you've calculated the resistor if this is exactly 0.7, but for a particular current. If this, you're forcing that current through here, so your VBE on will change. Maybe it changes to 0.701. That doesn't change the current through R very much. So if you use VBE on to calculate your R, it will generally get you very close to the current that you want, because this node right here doesn't change all that much. Has anybody read the lab handout? You know, the last step of design? Doing the sound game doesn't really work on Zoom, but it starts with a T, a W, an E, an A, a K. Yeah, tweak is a true, it's actually a design step. If you ask Dr. Prodnov, he says, oh yeah, you got to do the tweak step. So this will get you pretty close. Your current equation already is pretty much an approximation. When you ignore base width modulation, you're doing another approximation. This will get you close. It won't get you exact. But again, if your VBE on changes because of the current, it will only change just a very little bit at this node, and you'll still get pretty much the current you're targeting across your resistor. Okay, so let's do a couple more. Already half fast. Where's my mousey? Let's do a little bit more math on here. Not much, because there's really not all that much. But you said for your R, you've got VDD minus VBE on all over your, whatever your target current, and that equals your R. And then what other math? Really, that's all the math, I think, for this one. There's one more version of this. This circuit right here, if you design it badly, let's say, I don't know what might happen, but let's say you somehow set it up so you're getting way more current than you want. Current's a bad thing. Current hurts stuff. So you don't like to do that. So let me show you another version of this circuit. If I have space, I don't. Okay. Okay. This is, I'm just going to draw there. I'm not drawing ground yet. This pretty much, this looks like the same circuit if I connected these to ground. But turns out there's a little trick you can use to protect your circuits, and that is to put a resistor down here. And for this example, I'll just name them the same thing. Look at just a couple of things here. Let's do IC equals IS e to the VBE over VT. What voltage changes your current the most?
VBE.
VBE. So if your current runs away, it would be nice if something turned down your VBE current, your VBE voltage. Sorry. So let's see. Let's say you've got too much current going through here. I giant. Is there anything here that helps your circuit not burn up?
Bigger resistor?
Yeah, this resistor, how's that work?
Oh, I was thinking of our bias, but
That's true. If you have too much current, then that's going to drop your base voltage. That's true. How does this one work? How's this one down at the bottom work?
has a pull down?
Not a
Apparently.
It increases the emitter voltage, so VBE.
You have a big current through there. What do you know about that voltage?
The voltage across resistor. So if the resistor's high, then
Yeah, goes up. So if the emitter voltage goes up, assuming the base voltage doesn't move, which it does, but let's say it doesn't move. If the emitter voltage goes up and the base voltage doesn't, what happens to VBE?
Gets smaller.
It's smaller. So this is this can be considered a safety precaution, and it's called degeneration resistors. Generation resistors. And you say, my circuit has degeneration. My circuit has degeneration. I couldn't quite fit that in, but yeah. So this this right here will protect your circuits. It just happens that for the same reason it protects your circuit, it also kills gain. But we'll talk about that later when we get to the amplifier part of this. So you never, with circuits, one of the challenges is that you never get anything for free. So something that does good in one place is probably making something else harder. For example, if you want to make a digital circuit faster, what happens to power?
power consumption increases.
Yes. So you got it faster now, but now you're using more power. So there's generally trade-offs like that. And this one is another one of those. It protects your circuit, but it makes your amplifier gain go down. Okay, let's do, I'm not sure if they have you do math in your pre-labs, but let's, while we're here. So if you, I'm going to put, oops. I have trouble getting the banner out of the way. Nope, still not switching. There we go. Okay, so generally if you are using degeneration in an amplifier especially, you the size of these things are important. The bigger they are, the less your gain, but the more protection you have against too much current. So let me do this. I named them the same thing, but I'm gonna change that to R2 for the next discussion. And if you make R1 and R2, another advantage of using degeneration resistors is you can get the current through this side to equal a different current than this side. So if you wanted, I'm going to redraw it so I don't mess this picture up.
R1 and R2 are the degeneration resistors, right?
Yes.
So R1 and R2 don't necessarily need to be the same.
No. It's another trick where, so this biasing circuitry, all it's doing is generating a voltage so you have the current you want through your amplifier. We're treating this as a current source right now, but all it does is generate a voltage. And lots of times the thing that's actually doing the work is your amplifier. And if you have a lot of current through here, we'll call it IREF. It's really hard when I can't see your faces when I'm talking. Sorry if I'm missing things that you have questions on. But what you can do is since the bias, the calculation part, the biasing circuitry part of the circuit is not really amplifying or anything. It's not all that important for your circuit in performance. It's just generating a voltage for you. You can put a very small current over here and then put the current you want on this side by doing different values of R1 and R2. You can use just a little bit of current over here and as much current as you need for your amplifier in the amplifier side of your circuit. Is that confusing?
Okay, what was the purpose of this again? To have different currents through?
So this biasing circuit over here, it can actually be used in a whole bunch of other circuit. You can use this biasing circuit, let's call it RB. You can use it in, this generates your voltage, and you can use this RB in a whole bunch of other places for the circuit to use. Its job is just to generate that voltage. This and this and this are probably actually being amplifiers or you know, whatever circuit you're building. Those are the things that are actually doing your job. So if these have to use power, then you've got to give them the current that they need to do their job. But why waste power over here if you don't need to? And to do that, you can put a smaller current through your circuit that's just generating RB, and then use as much current as you need through your actual amplifiers. Did that clarify that at all? It doesn't look like it. So keep asking questions.
I understood everything you said up till the very last point you made. What was, sorry.
So these might need a lot of current. You could put that same amount of current over here, but now you're using 4I. And when you're doing a power equation, it's just supply voltage times current. So P equals 4IV for this, if all four of these have the same current. But let's say you can actually use like I over 10 in this part of your circuit. You still, in your amplifiers, you're probably going to have to use I to get the performance that you want. So these are still using I, but you can use a 1/10 of the current through this biasing circuitry and just use different R2, R3, and R4 to get the currents you need in your amplifiers. And then instead of P equals 4IV, now it's P equals 3.1 IV.
Okay, that makes sense. Thank you, Professor.
Any other questions? Can't tell. Emil, can you hear it now? Okay. Yeah, but the math for this is, oh, we're not going to get in the handouts, but this is probably more important. To figure out R1 and R2, you need an equation that relates R1 and R2 and your currents through the two sides of your mirror. So you have, let's call this IREF on this side and I out on this side, and we'll use R1, R2, and let's name this Q1 and Q2. Okay. So are the names okay? Right. Then we need to, circuits 1, when you did KVL and KCL, it's like, yeah, okay, that class is done, check. But KVL, KCL, that's what we're going to be doing the rest of the quarter. And so you need a loop that includes R1 and R2. And there's really only one. You want a single loop that includes R1 and R2. That's your KVL loop. And you have IREF times R1 plus VBE Q1. That gets you to here. And now you have to go back down. So you have minus VBE Q2 minus I out R2. And that all equals 0. Okay. Thumbs up. Okay. So now this is another one that's hard to explain. I'll give it my best, and then you can correct me. But if you just do this math and assume that VBE Q1 and VBE Q2 are VBE on, these cancel out. And all you get is IREF times R1 minus I out times R2 equals 0. And it turns out that, okay, just a second, I gotta let a dog out. It turns out that doesn't give you a good result. It turns out it'll be much less accurate than you need to be. So there's a trick. And the trick is to go back to this equation. And if you solve for VBE, first you get IC over IS equals e to the VBE over VT. And then you take the natural log of both sides, and you get VBE over VT equals natural log of IC over IS. And if you take it one more step, which I can't, you take it one more step, you get VBE VT natural log of IC over IS. Okay. Now it's hard to justify why you have to use this instead of VBE on, but the way I kind of the explanation that kind of satisfies me is for these different, for a different value of R1, it messes with your emitter voltage. And remember, this is super sensitive to a change in VBE. But just a small change there changes the current a lot. So when you're using a KVL where you're messing with the emitter voltage, this R1 will change the emitter voltage. You're doing that, you have to use a much more exact VBE equation. You can't just say VBE on. In other words, when you have a resistor that's messing with the emitter voltage, you want to use the more exact VBE equation. Okay. Oh, I got a thumbs up. Okay. Any thumbs down? Okay, so let's go one more step. We've got our KVL equation there, and we have a new new equation here for VBE that's more exact than the ones we were using. And now let's plug that into this equation and see what happens. So you have the IREF banner. Okay, so you have your, didn't change colors. Just a moment. Okay, so you have IREF times R1, that's not going to change. But now you have VBE of Q1. So you have plus VBE of Q1, and we know the equation for VBE over here. So VBE Q1 will equal VT natural log of, what's IC for the left side of your circuit?
IREF.
IREF. So that's going to be, remove this. Have your, man, this banner is just, how do you get rid of your banner for Zoom? IREF over IS. Now you have to go down VBE of Q2. So let's go down VBE of Q2. And on that side too, you have R2 that's messing with the emitter voltage, which is super sensitive. So you have to use the more exact VBE equation. So minus VBE Q2. It's also VT natural log. And what's the collector current there?
I out.
I out over IS, and then minus I out R2 all equals 0. Okay. Do you remember what I said last time about IS? About the saturation current? No. If you end up with an equation with the saturation current in it, try to get rid of it.
Oh,
We don't like a saturation current in our equations. Is there any way to get rid of it? What's log of A minus log of B?
Log of A over B.
So what can you do with this thing? Can't do anything with the IREF. That has to stay there.
You could change it into the log of A minus log of B form, and then it'll cancel out because you're subtracting the ln of I of S, and you're adding it with the two different ones.
So this right here, this is A. That's A. That's B. So you end up with VT natural log of
I ref over I out.
and you've gotten rid of your saturation current. You can't get rid of the current times the resistor stuff. But now you have an equation that relates your two currents and your two resistors. In this class, it's a designing class, kind of. We're getting there where we let you make more, where we ask you to make more decisions, not let you. And in this case, since current's so important, as a designer, you probably know your current. You probably picked a current for the reference side and for the mirror side. You probably have those two values. But that still means that you have an equation, one equation with two unknowns. So as a designer, what do you do?
Determine the resistance.
Yeah, but you've got two unknowns, and now you're a designer. I just gave you a promotion.
To pick one.
Pick one. Exactly. So it turns out that for degeneration resistors, somewhere between 50 ohms and like 200 or 250 ohms is a good size. So I would just pick one. And so again, you probably have your currents, since those are really important and they can destroy your circuit. But now you've got one equation and two unknowns. You just have to pick one.
I'm sorry. When you said you can approximate 50 ohms to 200 ohms, is that for either resistor that you can approximate that like within the range? Like you can pick R1 or R2 and then find the other one? Doesn't really matter.
Yeah, just remember that the right side of that circuit is going to be the right side of this circuit is going to be your amplifier, and the bigger R2 is, the smaller your gain is going to be.
Okay.
But again, the bigger the resistance, the more protection you have against runaway currents.
So we only have to worry about that. Like it's within that range that we can approximate it, but then like if you wanted a certain gain, like you wanted above a certain gain, then you'd have to take that into consideration when you're doing calculations, basically.
Exactly, well said.
Okay, thank you.
So yeah, degeneration resistances, if they're bigger than that, it's probably just going to destroy your gain. So if you have to pick an R1 and R2, try to get it between 50 and 200 usually. But depending on who your lab instructor is, it may go a little bit above that to 250 or something. So just as a review, all of this stuff that we did here was all to set a default current through your amplifier. So you say, well, wait a minute, if I have an amplifier, I'm gonna want to amplify some signal. But if this voltage right here changes, then you won't have that current through your amplifier, and your V out will be sitting, going back up here. Oops, wherever it is. Maybe way up here? Yeah. If you don't have the correct current going through your amplifier, you could be sitting up here or down here. So you want to keep that voltage on the base of your transistor. Let me just give you a preview since we used up the time on this. I used up the time on this. So now your circuit's protected. I'm gonna do this. And we're gonna turn this into a common emitter by adding a resistor here. We didn't have this part in my discussion today. But just by adding a resistor, now we have a common emitter over here. But this is a DC voltage, but you want to amplify something. What you do is, what's that capacitor do? Is it a low pass filter or a high pass filter? Does it let high frequency signals through or low frequency signals through?
Low frequency.
What's the other end?
High frequencies.
Yeah, it's confusing because it looks like it should filter out high frequency stuff, but remember that the voltage across a capacitor can't change instantaneously. So if this side moves fast, because the difference in the voltage between these two plates can't change instantaneously, this side has to move too. So this will only let the high frequency signals through. And what it'll do is whatever your original voltage on this node, it will just add the moving part of this signal through, not the DC part. So this is just to fill in that space. You're generating that DC voltage to put the current through here to get your V out to sit where you want it to. Again, you're setting a DC voltage here so you get the current through your resistor, so V out will sit where you want it to. But to put the signal that you actually want to amplify, you put this capacitor, this AC coupling capacitor. It looks like it's going to get rid of the low frequency stuff. Or looks like it's going to it looks like it's going to filter out the high frequency stuff, but it actually lets the high frequency stuff through. And just as, oh, I'm already over, but this side of your circuit is supposed to be pretty constant, generating a DC voltage. And if you put that signal directly onto here, it messes things up. So the final step, and this might be in 2 weeks. This is in 2 weeks for everyone. You'll add a resistor here just to protect this side, the side that generates a voltage. Just add resistors. Shoot, somebody's coming into the yard. To protect the biasing circuitry. That's where you're going in 2 weeks. But just this week, we're just trying to put that current through your amplifier so your V out sits where it should. Any questions? I guess we weren't going to breakout rooms this week, this time. I guess that's what I've got.
Thank you, Professor.
All right, thank you.
Thank you, Professor.
Thanks, Prof.
Thanks.
see what who's my dogs are attacking. I'll be back in a minute. Hi all. If you want to read, I'm not sure if, well, it looks like you do, but I'll send it again just in case. I think you all have it. You probably already got an email also. But moving to credit, no credit for up to 16 units. And then I guess for in major and support classes, and then I'll close the door. And then anything over 16 units in major and support classes, I think you have to take for a grade. But all GEs are credit, no credit. I think that's it. So I have a question for you. How many of you couldn't make the 2 to 3 time? Do all of you have something at the 2 to 3 time?
I can make it.
I also could make it.
Yeah, I can make it as well.
I could make it.
Me
I
too.
could make it.
I can make it.
I can make it too.
Is there anybody that can't make it? Okay. We'll see. I forgot to remind people the questionnaire on Polylearn about what day to have homework due. That is Sunday's winning, which I thought was interesting. I see some unhappy faces on that one, but yeah, Sunday's winning on that. I realized when I started the last lecture they don't have the homework posted for this week, so sorry. I'll do that right after. Well, I'll do the doggy walk and then I'll get that posted. Yeah, but we'll see when that goes for this week. Friday, Saturday, Sunday, somewhere around there. We'll figure out when it's due.
Oh, were you gonna have the class 2 to 3 and just have everybody in it, or?
I was thinking then we could just do problems for 3 to 4 or something.
Okay.
But I know that there were some people that said they couldn't do that time, but there was 42 for the last section. And 52, 57. So there's like 10 people that didn't come to class today. Yeah, with this credit, no credit thing, I think I'm gonna count when people show up. So try to come to lecture. It's our only contacts. I mean, there is office hours, but try to come to lecture if you can. And if at the end of the quarter, if somebody's close to a higher grade or close to passing or not passing, and they've come the entire time, I'll move them up. But if it's like, if they're, close to not passing and they haven't shown up, then I won't be as kind. Okay, so try to come to class. I'll figure you're getting stuff from class, so you should get credit for whatever you're absorbing in class. Yeah, I mean, if you miss a few, it's no big deal. But okay. So how many of you actually had a lab last week where you did the characterization? All right, a few. Because there's the labs are in different places now, as usual. I was gonna cover current mirrors on Wednesday, but to give you the opportunity to ask questions and to give you like a first view, let's do it today. So lab might be a little bit friendlier. The reading for this topic is posted. It's my lab handout. If you do the reading at the beginning, consider that the reading for this week, or for the first half of this week. See, anything else that I need to talk about? I'm sure there are. Oh, my headset was supposed to have already arrived today. It's not here yet, or else my dogs ate the messenger. But once again, sorry. Okay, all right, then let's start. Okay. As mentioned, this class is called Analog Electronics and Integrated Circuits, but really it's all about building an op-amp. So we talked about the different stages last time, and what stage did you see this circuit in?
You're not sharing your screen with us.
Oh, good point. Okay, share screen. Details. Yeah, first day of 307. Darn, the projector's not working. And figured out I had to plug it into the computer. That helped a lot. Yeah. Can you see okay now? Okay. So what's the circuit?
This is a common emitter.
Common emitter, yeah. So you look at the three terminals, you've got a base, collector, and emitter. The base, it's not a common base because VIN's connected to the base. It's not a common collector because Vout's connected to the collector. The terminal that's left is the emitter, so this is a common emitter. We haven't got to MOSFETs yet, but what would this circuit be?
Common source.
Common source, exactly. And these are both the highest, well, not the highest gain, but most commonly used gain stage. So let's look at the common emitter. Move the common source out. Well, you don't really need to. Okay, so this circuit, as you saw in 307 when you were calling it an RTL, it looks something like this. Okay. Let's say VIN is 0. What's V out doing?
It's at VCC.
Right, VCC. Is that exciting as an amplifier?
No.
If you change V in, V out isn't changing at all. So that's 0 gain. Okay. What if I make V in really high? Like it's conducting a massive amount of current.
Then it's 0. V out is 0.
Then you're over here. Is that an exciting range for amplifiers?
No.
So one of the first things that you have to do on an amplifier is somehow set a default current that puts it in this region over here. And just for today, this is not how we're going to calculate it, but let's just use VDD over 2, for example. So if you could get the default current going through your amplifier to equal a current that puts you right there, then that's pretty good. If the current goes up, then you move this way. If the current goes down, you move that way, and you right in the amplification region, you get gain going in either direction. So that's good. Okay. One thing you know, let's say you're targeting your default current here to set it at VDD over 2. You also know if this is VDD, if this is VDD minus I times R. Do you agree with that? Yeah, so if you want it to sit right there, the default, you need to have a current going through this that subtracts VDD over 2 across the R. Okay, so let's figure out how to set a default current through your amplifier. And I have a slight pet peeve with how this is presented in lab and all, because it's presented as a current source, which it is. This is what you use as a current source if you want a current source in your circuit. But right now, the whole reason why we're introducing this next circuit is to set this default current through your amplifier. You're trying to set that initial current so you're sitting in the middle of the amplification region. Let's see how you do this. Okay. So a couple of questions here. This is not a common emitter amplifier. Why can you tell right off the bat it's not a common emitter amplifier?
Base is connected to the, oh wait, excuse me.
No, you got it. Yeah, the base is connected to the collector. And this thing right here is called a diode connection. And if you have a MOSFET and the gate's connected to the drain, you also call it diode connected. Or diode connection or diode connected. Okay. Next question is, if there's current going through this circuit, we don't know what it does yet. What region of operation is it in?
Is it inactive, forward active?
This voltage right here, approximately, what is this voltage?
VBE on.
And VBE on is always bigger than VCE sat. So this node right here will always be, this voltage right here will always be greater than VCE sat. And you know this transistor is in the forward active region. Okay. So this circuit, I wrote VBE on over here, but it actually isn't. A good approximation of that VBE is VBE on, but it's not exactly VBE on. Pretty close though. How come it's close? That's a very random question, not well asked and not well boundaries. Why do you know it's near VBE on? What happens if that VBE goes much larger than VBE on?
Do things just start breaking?
Yes, why do they start breaking?
Because there's too much current and it gets too hot.
So just a small change in VBE changes the current a lot. So this isn't VBE on, but it's going to be pretty darn close. Okay. So if this voltage across the base emitter is VBE on, what's the voltage at that node, at the collector? What do you think? This is shorted, so if that's VB on, you know that that's also VB on. Okay, so we've got this thing pretty much figured out. We know the transistors in the forward active region. We know the base emitter voltage is about VB on, but not exactly. You know that since this is shorted, the base to the collector shorted, you know the collector voltage is also VB on. Next step is, let me step away from the values on this circuit for a second. There's a magic thing that happens. If you have a transistor in the forward active region and you force some current through it, whatever it might be, if you force some current through this transistor, this VBE goes to exactly VBE for that current. So far when you've looked at transistors, you've set the VBE and figured out the current, but it turns out if you force current through a transistor, the VBE will go to the correct VBE for that current without a voltage supply or anything. Just force that current through that transistor, the VBE will go to the correct current. And you can kind of see that you've got your IC equals IS VBE over VT. IS is a constant, E is a constant, VT is a constant. So if you force IC, then VBE is going to go to the correct value for that IC. Okay, so let's say I wanted to have a particular current, approximately a particular current through that resistor. I know the voltage at this end's about VBE on. How do I get that current? Another slightly random question, but this is the information you have. How do you force a particular current? Call it IREF through that resistor.
Would you set that current equal to, or, well, I guess you would do current times VDD minus VBE on to get R. Or excuse me, that over I. Wait. Yeah, you would do you would do that, yeah.
So if this is approximately VBE on, this will approximately give you the R that will force whatever your target current is right here. That it'll force that target current through your transistor, and your VBE on will go to the VBE on for whatever that current is. Does that make sense up to there? Okay, so by knowing this is about VBE on, you can force a particular current through your resistor, and there's no place for that current to go except through your transistor. So you're forcing that same current through your transistor, and then the VBE of that transistor magically goes to the VBE for that current. Okay, so here comes depending on who you have for lab, they may word it differently, but I call this like the biasing circuitry. And then if you take this VBE and you put it on another transistor that you know is in the forward active region, this has to also be in the forward active. So if that's in the forward active region and you put the same VBE as you put on over here onto this transistor, what do you think happens to the current through the transistor on the right?
The same.
The same. So what's the current through here?
IREF.
IREF. Usually just by tradition, they call it I out, but in this case, I out would equal IREF. So the left side is there to generate a VBE for a particular current. And then you can use that VBE on a whole bunch of other transistors to get that same current, to reproduce that current. And this side is generally called a mirror. Okay. I'll post all these notes up, but any questions up to here? So let me, sorry, I'm moving that off. Do you want me to move that back? Did everybody get that? Yeah.
I just had one quick question. Would the base need to be connected to the collector on the mirrored side as well?
As long as it's in the forward active region. And these two transistors right here have to be the same model, the same type of transistor. The VCE, if you look at this graph right here, this is VCE, this is IC. It really doesn't matter what VCE is. It gives you approximately the same current. So as long as you're over here in this region, this voltage here doesn't matter much. As long as the VBEs are the same and they're both in forward active, you get approximately the same current through both sides.
Okay, thank you.
Okay. Does this side look like a common emitter?
Yes.
Part of it. What's it missing though?
Resistor.
Resistor. Yeah. So this generates the current in the lab manual or the lab notes. This is usually called our bias, and that's called our load. So now you have a common emitter amplifier. What's missing? What really important thing is missing here? You want if you're making an amplifier, you probably want to amplify something. And right now, all we've done is set a DC voltage. So V out will sit kind of in the middle of the VTC. Now, all we've done so far is set a default current through our amplifier, but we're not amplifying anything. So this is actually not this week. Next week, you'll see this in lab. So this is jumping ahead. Without seeing the whole story, this biasing kind of seemed weird to me when I learned it. So let me give you like 2 weeks ahead here. If I do this, so if I have a V in signal, does the DC get through? Does DC go through capacitors? Oh, I see people shaking their heads. That's the right answer. Yeah, so this could be at 100 and 100 volts. This will probably be around like 0.7 volts here. Is there any problem if this is sitting at a DC 100 volts? Yeah, as long as the rating of the capacitor, so the capacitor can have that much voltage across it, this is totally fine. What if I put a little sine wave on top of that? So it's actually going like to 100.1 and then down to 99.9. And that's a fast signal. Does the fast signal get through? Yes, so just this signal will show up and get added to the 0.7. So when it goes through the capacitor, what you'll get is whatever voltage this side is setting it to, this 0.7, plus this. So now you'll be sitting here and that signal coming through will move you up and down a little bit. So that's going to be the secret in next week. You'll add this. There's one problem with adding this capacitor, and this is called an AC coupling capacitor, or it's also called a DC blocking capacitor. The one thing about this is this side is it's like a voltage source. It's a DC source. It doesn't like having moving signals introduced to it, and that's what this does. This is directly introducing a moving signal. So you'll see next week or the week after, you'll add resistors here to protect the left side of your circuit. So this moving signal right here doesn't go that way. It only goes into your amplifier. That's not for this week. For this week, you're just worried about setting a default current through your amplifier. You're worried about that much of your circuit this week. Okay, up to there, good? What time is it? Oh, we got lots of time. Right, so let's do one more step here. Again, what hurts circuits?
Current.
All right. So in this case right here, if there was runaway current, if you accidentally set your VBE too large or something like that, this thing could fry. So there's actually a way to protect your circuit. I'm not drawing in ground yet. Again, next week, this will be turned into a common emitter by putting a resistor up here, but for this week, we'll leave it like that. Oh, I remember what I forgot to put in the other, forgot to do in the other class. BI out, ref. Okay. These are called degeneration resistor. And this circuit is degenerated. What's a word that sounds like this that you saw in 307 that doesn't mean this? You remember regenerative circuits? Not so much? Okay.
They like restore the voltage state.
Yeah. Okay. So these degeneration resistors, let's say you had too much current going through here. What would R1, how would R1 protect your transistor?
It would limit the amount of current able to flow through the transistor and direct it off to the other one.
Won't direct it off, but it will definitely control the current through the transistor. But how does it do that? What's the most important? Oh, pen stopped working yet again. There we go. Ah, that's weird. My pen's weird. What's the most important voltage in the current equation?
VBE.
Exactly. So if you have a lot of current going through R1, what happens that might turn down your current?
Lower VBE.
Lower VBE, and how does that happen?
Increasing the voltage drop of R1.
So this voltage goes up. So what happens to this node?
The emitter voltage increases.
Emitter voltage increases, and it's not true, but assuming the base voltage doesn't change, then what just happened to VBE? So if the base voltage doesn't change, but the emitter voltage does, the emitter voltage goes up, what happened
It's
to VBE?
smaller.
Yeah, so this is a nice little safety safety feature. Does that sound like good English? Safety feature. And you say, well, great, this just saved my transistors from frying. But in circuits, you generally don't get anything for free. So for example, in 307, when you wanted a circuit to run faster, in other words, have a higher rise or fall time or something like that, you increase the current. But when you increase the current, what happened? What bad thing happened?
More power dissipation.
So that was a trade-off between speed and power. Same thing here. It turns out if you, remember, we're going to be turning this side into a common emitter by adding a resistor up here. It turns out that if you put a degeneration resistor on your amplifier, it kills the gain. So you protected your transistor, but oops, you just killed your gain. So in general, these degeneration resistors, you generally see them between like 50 ohms and 200 ohms. 200 ohms, you're really hurting your gain. But 50 ohms, it's enough to protect your transistor in most cases, but not kill your gain all that much. So it's one of the things when you're designing, if you want a big gain, then you want to reduce your degeneration resistors, degeneration resistor sizes. Is that okay how it works as this little safety feature again? And it's pluses and minuses. Okay, so let's go to the last thing I want to say about this is call this Q1, Q2. So when you use degeneration resistors, another thing you can do, it's not only just a safety feature, it's also it lets you set I ref not equal to I out. And sometimes you want that. As an example here, let's say we had R1 equals R2, then the currents through the two sides would be equal. And then when you figure out power, it would be 2I times VDD. That would be your power. You have that current going through this side, and you have it also going through this side. So that's where the 2 comes from. And whatever that current is times the supply voltage, that gives you your power. But what if I could make I ref 1/10 of the size of I out? So let's say there's a case where I ref is 1/10 I out. So case 2, make this case 1 I ref equals I out. And then case 2, I made I ref equals I out over 10. Usually with your amplifier, there's a certain amount of current you need. But for the biasing circuitry, it's not the thing actually doing the job. It's not the thing actually doing the amplification or filtering or whatever it might be. So what if I made I ref 1/10 of I out, what would my new power be?
11/10 IVDD.
11/10 are VDD. And you've almost halved the power now by using less power in the biasing circuitry than your actual amplifier. So there are times when you want different currents in both sides. I don't think, I don't think you'll use it in lab. I'm not sure though. It all depends on who the instructor is. But when you're doing that, if you want the same current in both sides, you just make R1 equal to R2. But if you do want different currents through the two sides, then you have to do a little bit of math, just a little bit. And let's look at that. Circuits 1, KVL coming back at you. The rest of this class is going to be using KVL and KCL. So let's look at KVL. And I want something that relates R1, R2, I ref, and I out. Those are the things that I want to change R1 and R2 to get different I refs and I outs. So I want those in my KVL equation. So I see this loop right here. It gets both R1 and R2. And so that looks kind of promising. So let's try to find the KVL for that. Right, so this KVL, what's the voltage from ground to this node?
I ref R1.
I ref R1. And then we have the VBE of Q1. And then that brings us to this node. And now we have to go down the other side. So we go down the VBE of Q2. And then we have to go down the voltage on R2. And what's that?
I out R2.
And that all equals 0. Okay, so far we've just been approximating VBE as VBE on, but if you do that here, then these two terms just cancel out. And this is really hard for me to justify, but I'm going to try. This calculation, this KVL, this R1 and R2 is actually changing the emitter voltage. R1 and R2 are actually messing with the emitter voltage, and just like you when you were looking at degeneration resistors and why they protect against current runaway, that they change the emitter voltage, therefore turn down VBE. For the same reason, right now in my KVL loop, for different values of R1 and R2, that's going to change the emitter voltage, and now your VBEs are going to change. So R1 and R2 are changing that VBE, which changes the current a whole bunch. So just using VBE on as an approximation doesn't really work here. So let's look at what we have to use for VBE here. We'll start with IC equals IS e to the VBT over VT. Now I want to come up with an equation VBE equals something. So to get to a VBE equals something, I'm going to divide both sides by IS. So I get IC over IS equals e to the VBE over VT. Get that right? Yeah. And then I'm going to take the natural log of both sides. So I get VBE over VT equals natural log of IC over IS. And when I solve for VBE, I get VT natural log of C over R. Yes. Do you agree with that one? Okay. All right. So this equation right here is more accurate than just approximating as VB on. More accurate than same. And in this equation, again, since we're messing with that emitter voltage, we want to be more exact with our VBEs. So let's take this equation and we'll do the IREFs. They're there forever. Let me go back to green. So we're going to take this equation and mess with it. We have our IREF R1, and then we have VBE Q1. So we have to use that more exact VBE equation. So we know that's VT natural log of IC over IS. So that's VT natural log. What's IC on the reference side?
IF.
IS. And then we go down VBE Q2. And we want to use the more exact VBE equation again. Natural log of, what's the current on the mirror side?
I out.
Minus I out R2 equals 0. Okay. All right. So we're almost there. Do you remember last week when I said it was last week, last Friday, when I mentioned having saturation current in your equation? Do you like that? No, we don't like IS. So if you can get rid of the saturation current from your equation, it's good. Do you see any way to get rid of saturation current in this equation? What's that equal?
Log A over B. Over log B. No.
Does that help any?
Yeah, it should cancel out, right?
Yeah, IS's cancel out. So then you get I ref times R1 plus BT natural log. This is going to be A right here. That's going to be A. That's going to be B. So you get I ref over I out minus I out R2 equals 0. Okay, so this is a single equation with 4 unknowns. Can you solve it? I think that's the right answer. No, you can't. So you can't solve this for R1, R2. You have 4 unknowns, R1, R2, I ref, and I out. If you are a designer, you probably already picked your I ref and your I out. So those are values you already selected. So you know those two, but that still leaves 2 unknowns. And the 2 unknowns are R1 and R2. This class is supposed to be more of a design class. So you all are designers. As designers, what would you do at this step?
Maybe simulate it and try different R values.
Oh, you could do that. That's a good answer. But Yeah, try different R values. Basically guess. So what do you know about degeneration resistors? What information do you have so far?
They should be between 50 and 200.
Like that, exactly. So you can just pick one of these and make it 50 ohms, and then you can find the other value. So you as designers, at some point, you're going to have to pick current, and you're going to end up with these equations with more than one unknown. You just have to, from your knowledge, pick a value and then go with it. And then, just like Sean said, then you simulate and you see if it worked. Some things you might take into consideration there is that, remember, this right side is going to be a common emitter amplifier, and the bigger R2 is, the smaller your gain is going to be. So that might be something that you take into account. If you know that you're building a circuit that may run into too much current, then make your resistors bigger. Okay. Let's see. There was something I remembered. I remember. Okay, this is a bonus because the other class didn't get it. When up here, when we calculated R bias, that's right here. So this is actually R bias. And this would be R bias. This is a nice friendly calculation. And you realize that you've got a VBE on that the transistor eats up, and you've got your supply voltage. In lab, I think it's 10 volts. Is that right? I think. Oh, okay. So it's 10 volts, and then whatever VB on is like 0.7. So you have to drop like 9.3 volts across this resistor. Okay, let's go down here. What's comparing, let's see, what's the voltage drop across the transistor here, approximately?
VBE.
VBE, and in this case, you can say for finding R bias, and this other thing helps you with the degeneration resistors, but to find R bias, once you find R1, there's a little trick you can do. But yeah, this is still, you can still approximate this as VBE on when you're trying to find R bias. If you keep R bias the same size as above and just add R1, your current's going to go down. You won't get the same current as your previous circuit. You want to keep the same current. So if, let's say up here, you found a great current, everything's working great, but then you say, oh, I just want to protect my amplifier, so I'm going to add degeneration resistors. If you come down here and want to keep the same current because your amplifier was working great, you still have the same voltage drop across the transistor, which means the voltage drop across R bias plus R1 has to still be your 9.3 volts. Can somebody say that better? Or so do you agree up here? If this is 0.7, then you have to drop 9.3 volts across R bias. Okay. And down here, you still have 0.7 volts drop across the transistor. Across the rest of the resistors, you have to drop the remaining voltage, which is still 9.3 volts. And if you have the same current, let's say you got 9.3K for this one. for your original R bias. And then you made R1 100 ohms. What would you have to do to R bias to get the same voltage? Oh, this I'm killing this question. I'm destroying this question. How do you get for the same current? Let me do this way. Okay, original R bias equals 9.3K. Okay, now you've added R1. What do you know about the sum of R1 and R bias? You're going to have the same current going through, same IREF. And
They
the
should
same,
equal the original resistance.
it should equal the original resistance. This might not feel right now, but your R bias prime, your new R bias equals your original R bias minus R1. Okay, that might be fuzzy, but hopefully somebody, if you have questions in lab, I can stay on now and answer more questions. I think it's 4 now, but I'm happy to keep talking. But yeah, I cut that last little conversation a little bit short. Any questions on that? No? Okay. And hopefully that'll get you ready for lab. That'll be good for lab. And then we'll finish the small signal model on Wednesday. Okay.